It's a pre-lab video for Physics 2213 for the experiment, the Verdet constant and Lockin amplifier. So when you come into the lab, this is what you will see. You will see an optics setup, although you'll have to do most of the optics setup. You'll recognize the laser and a couple of steering mirrors, a neutral density filter. There'll be a linear polarizer inserted here. You'll have to insert. And we go down to the other end of the optics table. We see our photodetector and another polarizer. But in between, we see this device. This is a solenoid. This solenoid carries electrical currents, and the electrical current, as it goes around a solenoid, generates a magnetic field that's axial to the solenoid. So the solenoid, inside the solenoid, there'll either be a magnetic field in this direction or in this direction. Well, in our experiment, we're going to be driving this current with an AC current, meaning the current will be flowing first in one direction and then in the other direction. So the magnetic field will be oscillating between going in this direction and going in that direction. Okay, let's get you familiar with some of the electronics you'll be using. So to create the oscillating currents, you'll be using a function generator. And of course, we've used the function generator before. It's in its usual location off to the side there. So our function generator we'll be using. Because we're going to be having a time-varying signal, because the function generator is not providing a DC current, it's providing a time-varying current, we'll be, by and large, viewing the signal on our oscilloscope. Okay, but the function generator on its own doesn't provide enough current to our solenoid to create a large enough magnetic field for us to see the effect that we're interested in. And so we have here an amplifier. And this is an audio amplifier. It really is just an audio amplifier that you would buy to power your speakers, except here we're increasing the current going to this solenoid rather than going to some acoustic speakers. So it will be controlled by a power switch on the front, and as detailed in the lab manual, you'll just increase the volume knob. And as you increase it, you see these blue LED lights increase. And what we want to do is set up for 1 amp worth of current going through the solenoid so that we can understand how much magnetic field we have running here. And so to do that, we'll be monitoring the AC current using our digital multimeter. Now, a digital multimeter will have to be in AC current mode. And you'll notice that there's only one current mode here, amps or milliamps. But because we'll be having a reasonably high current, we'll be on the amp setting. And to distinguish between DC and AC current, when you have it set to the amp setting, you have to push this select button. And that will allow you to select between, I'm not sure, you probably can't see this, but to select between DC and AC by putting the select button on. Okay, so we want 1 amp of AC current. Okay, and so what's that going to do for you? It's going to create a magnetic field. Big deal. What is inside this solenoid is a special material, a special glass rod, which can change the angle of polarization of incoming light, or light that passes through that rod. It will rotate the angle of polarization of light passing through that rod. So if light is polarized vertically, as it comes through, it'll come through the rod and it'll get rotated. The amount by which it gets rotated depends on the magnitude of the magnetic field. In no magnetic field, you get no rotation and the polarization just stays what it was. In some magnetic field, this gets rotated, and in a bigger magnetic field, it gets rotated more. And so that's what we're going to be doing. And rather than just increasing the current in here, the DC current in here, and looking at this change in rotation, what we're going to do is have a time-varying current in here. Now, the purpose of that is so that the signal that you receive will also be a time-varying signal. But you'll know something about the properties of the time-varying signal on this photodetector. It will be varying at the same rate at which you at which your function generator is set. So if you set the function generator to 45 hertz, then the signal on your detector will be at 45 hertz. meaning you can disregard any signal on the detector which isn't at 45 hertz. So any sort of 60 hertz or 120 hertz noise from the lights, or whatever frequency these lights are flickering at, can just be rejected because it's not going to happen to be at the frequency that we set our function generator, or it's unlikely to happen to be at that frequency. The other factor is the phase of the signal. Even if there was a noise signal at, say, 45 hertz, we can reject all of the 45 hertz signal as noise if it doesn't occur at the correct phase with respect to our drive. And you'll understand a bit more what that's doing when you try and program up your own lock-in amplifier using LabVIEW. And so again, read the lab manual carefully for what a lock-in amplifier does. It basically allows you to pick out a signal on your detector at the correct frequency and correct phase for what you would expect. And meaning you can be looking on an oscilloscope and seeing a very, very noisy signal, but you can actually extract the component of that noisy signal, which is what you call your good signal, or the signal that you reject all other signals except for your good signal. And it's a very powerful tool for seeing very small signals in a very large noise background. And so you'll be using LabVIEW to create a software lock-in amplifier. So you'll be given some starting point for your program, probably something like this. And I'm not sure how much you'll be able to see on this video, but this is the LabVIEW interface, which you've used in the past. This big block here is a while loop, and any parts of the code which are put inside this while loop will just run over and over and over again. So it'll just cycle through whatever code is in here. So it'll execute all the commands and then go back and re-execute all the commands and keep looping through until you press the stop button, which is on the front panel. So remember, LabVIEW programs have the block diagram, which is where you write the program, and they have the front panel, which is what the user sees when they run the program. So you get a reasonable starting point for this program. You just have to, following the instructions in the lab manual, create your own lock-in amplifier. And what does that mean? Well, we're going to have to read the signals from the scope, we're going to have to read our detector signal, and we're going to have to read our reference signal. And so we'll have to read those from the scope, and so we'll use this read scope sub VI, which is created for you. And of course that'll have to be inside the while loop. And we want to use the error signal to control the flow in the program, so we'll just wire up the error signal. And if the first thing we want to do inside the while loop is read the scope, well, we'll read the scope. We'll wire it up to be the first thing. Now, you want to turn on the context help feature so that when you hover over any item, it'll tell you some information about it. And remember, the way these VIs work is wires that come in on the left of the VI are generally inputs, and wires that come out of the right of the VI are generally outputs. So this read scope VI takes as an input this error in control, which is basically just the flow of the program. Okay, when it's this VI's turn, it'll execute that, and it takes in what channel you want to read, and then it'll output just the waveform from that channel, the list of numbers corresponding to the voltages at the different times. And the different VIs that you hover over take different things. This is the phase shifting sub VI that you're going to be using to build your lock-in. This is the sub VI that's going to do the averaging for you. A lot of these inputs don't actually have to get wired up, just the signal in, and you'll just be looking at either the RMS or DC value on the output, whatever is relevant. And away you go. So you'll have a reasonable amount of time here to set up this program. You'll be working with a partner while you're creating this program. And so I hope that given your previous experience with LabVIEW and the fact that this program is partly set up for you, you shouldn't have to add, well, you may or may not have to add any new things onto the block diagram. A lot of it already exists. And so anyway, I hope you find this a fun exercise, but then once you create this lock-in amplifier, you're going to test the power of this technique by going back to your Verdet constant experiment and seeing how much easier it is to get a signal out of your lock-in amplifier than it was to attempt to try and observe the signal on the oscilloscope and do a measurement directly on the oscilloscope. So this is basically replacing the oscilloscope as the measurement tool. Okay, great. So Lockin amplifiers, powerful devices for pulling small signals out of noisy backgrounds, and really an important fundamental concept, and it won't be the last time in your undergraduate career here at York that you'll see them. So getting a nice introduction to the fundamentals of how they work in this lab, I think, is very important. All right, good luck.